All right. So now we're going to talk about molecular compounds. The other ones we're dealing with when a metal donates an electron and the other particular compound takes the electron. Okay, the non-metal takes the electron. Now we're going to be moving into something a little more different. We're going to talk about molecular compounds. Molecular compounds is when they are actually sharing electrons, when you have two nonmetals sharing electrons. The name of these molecular compounds are going to need prefixes because several different compounds can be formed with the two metals. We're going to learn a little bit more because we will learn that around the semester that most of the time you can use carbon oxygen. You can have different types of carbon oxygens molecules. So we're going to have to name them differently. Okay. So here we have an example we're going to get into. We have a carbon and we have an oxygen. The way we're going to name this particular one, we're going to say it's going to be carbon. The rule of the nonmetal is going to, it's going to happen again. The second nonmetal, we're going to switch the name. So we're going to go from oxygen. Again, we're going to switch that into oxide. Okay, very similar to what we did with the nonmetal before. The only difference is now we have to worry about the prefix, the subscripts. If you have a subscript, then you have to put here a di. So that's going to let us know we have two oxygens. It's going to be carbon dioxide. Okay. Here we have carbon disulfide. The sulfur, it has two of them, so we have to put the di. The same thing happens when you have in the first one. Nitrogen is going to be dinitrogen oxide. Again, example, you have dinitrogen dioxide. Then the reason why we have to put it because nitrogen can also be nitrogen oxide. It is a valid structure. Okay, so that's what we have to worry, and we're going to have to add prefixes to it. Okay, we're going to have to add prefixes in order to fix this problem. We're going to have to be able to do this. Okay, so covalent bonds are going to be what we're going to be dealing for now when we share electrons. So molecular compounds are formed when atoms of two or more nonmetals share electrons to form a covalent bond. Valence electrons are shared by nonmetals to achieve stability. You're not longer taking, you're sharing. Okay? A molecule forms when two or more atoms share electrons. One of the things I want to go over is we have to be careful. Okay? We sorry. We're gonna have to go over those prefixes. When naming a molecular compound, again, the first non-metal in the formula is named by its element name. Again, what we did with the non-metal, the first non-metal is going to have the same thing. The only thing we have to be careful is there's no subscripts. Okay, if there's subscripts, then we have to start. I'll show you what we're gonna have to do. The second metal, the non-metal, is named by using the first syllable and its name followed by the I. Remember when we talked about oxygen, we went to oxygen to oxide, nitrogen to nitroxide, all those different ones. Okay, or fluorine to fluoride, bromine to bromide. Now we have to be careful. There's one more thing we have to be careful for this particular one. When a subscript indicates two or more atoms of an element, okay, a prefix is used in front of the name. And here are the prefixes. There's one exception, and I'll try to go over it, but mono usually gets dropped. One, we usually don't put it in there. When we start carrying this, when you have two. When you have two, it's going to be di. Three is going to be tri. Four is going to be tetra. Five is going to be penta. Six is going to be hexa. Seven is going to be hepta. Eight is going to be octon. 9 is going to be nana, and 10 is going to be deca. Okay? Those particular ones. And there are some things, well, some rules that I'm going to go over that you have to be careful. There are some rules that we have to watch out for, and I'll show you which ones are those. Okay. Several compounds may form the same two nonmetals. So this is what we have to put this prefixes. I already showed you. Okay. We talked about this one here. We have nitrogen oxide. Believe it or not, we can have a nitrogen with two oxygens. So what do we do here? We're going to put the nitrogen and we're going to put we're going to put the dioxide. And believe it or not, nitrogen can bind to three oxygens. So we're going to have nitrogen trioxide. So that's what we have to add the prefixes so we can let the reader know that this is which one it is. Because if we write nitrogen oxide and we don't have the prefixes, then we have three possibilities we're going to be dealing with. Okay. The number of oxygens in an atom presents indicates by the prefix. That's something we have to be careful. So di, tri. Mono, but we dropped the mono. Another rule we have to be careful that I want to go over with you guys. When the vowels O and O or A and O appear together, the first vowel is omitted. We're going to drop the first vowel. Okay, that's going to get dropped. All right, so that's another thing. I'll try to show you a name of I'll try to show you an example what this is going to happen. In the name of the molecular compound, the prefix mono is usually omitted. This is where I remember I told you we usually put it. So omitted. As in nitrogen oxide, we don't put it. There is some exceptions, okay? The exception is this one here. This is going to be carbon monoxide. The reason why, because it's always been known as carbon monoxide before the language was invented, so that's why we stick with carbon monoxide. Okay. Why do we care? Common molecular compounds because they're present everywhere. Carbon dioxide is used in fire extinguishers, dry ice, propellant aerosols, carbonation of beverages. Okay. Carbon disulfide manufactured on rayon. Dinitrogen oxide is an inhalation anesthetic or laughing gas. Okay. Nitrogen oxide is a stabilizer biochemical messenger in cells. This is more biochemistry, biology type. Sulfur dioxide, preserving foods, vegetables, disinfecting breweries, and bleaching textiles. Sulfur hexafluoride, electrical circuits. Sulfur trioxide is manufactured of explosive. Again, we're going to go over how to name molecular compounds. I'll give you an example. So let's see, I gave you this particular one. The name of this molecular compound, you're going to have a nitrogen and 3 bromines. How do you break this? Okay, analyze the problem. Find the symbol of the element. Okay, that's the first thing I want you guys to do. Break them down. So you're gonna have the first one, nitrogen and bromide. Okay. Again, the first one keeps the same name as the element. The second one, you have to switch the ending to IED. Then you have to figure out if there's any subscripts. Okay. This one has 1, so you don't have to deal with it. Okay, except for the carbon monoxide. Okay. Then bromine has 3, so you have to use the prefixes 3. You put the name together. Okay, so name the first nonmetal by its element name. So that's going to be, first is going to be nitrogen. That's the first one. Step 2. Name the second element of the first syllabite by its IAD name. So it's going to be second nonmetal, it's going to be bromide. Then we're going to add the prefix to indicate the number of atoms and subscripts. Nitrogen we don't worry because it's 1, but the bromine does. Okay, because there is 1 nitrogen, no prefix is needed. The subscript 3 is needed because atom shows a prefix of 3. So it's going to be nitrogen tribromide. And that's how we're going to name molecular compounds. Okay. molecular compounds. And don't get them confused, okay? Ionic compounds and molecular compounds are different, okay? Even the way they are put together, they're different. One is covalent, the other one is ionic, okay? This one share, the other ones don't. One takes, the other one shares. Okay. Sometimes there are going to be some ones that some other are going to be confusing. There are some. We're gonna run into a problem. Okay. How do you determine if something is ionic or molecular? A compound is usually ionic if the first element in the formula is named a metal or a polyatomic ion NH4 plus, the ammonium one. Okay. So that is going to determine. Okay. Here we have what we call potassium oxide. So it's a metal, so it's going to be ionic, so we name it potassium oxide. Molecular, if the first element in the formula is a nonmetal, so it's the nitrogen dinitrogen oxide, so it's going to be a metal, so the compound molecular is going to be dinitrogen oxide. Okay, that's how we determine if it's ionic or molecular. So far, what have we learned about naming ionic and molecular compounds? So ionic metals are going to be something that is a metal or ammonium. Okay, that's the cation exception. Okay, that is a nonmetal with a nonmetal. Okay, first only the positive ion forms more than one positive ion. That's the other thing we have to be careful. Those elements that are transitional are going to have more than one positive ion. So we're going to use the name of the ammonia element or ammonium. Use the element followed by the Roman numeral if it's one of those metals that it could do more. Okay, that could do 2 or 3, whatever it's going to share. All right, now we have two types of nonmetals we talked about. We talked about the monatomic metals, sorry, the non-monoatomic ions, and we talked about the polyatomic ions. Okay, use the first syllable of the element, and they're going to follow by ion, and use the name of the polyatomic ion for the polyatomic ions. So that table is going to be important. Molecular compounds, when there's two nonmetals, that's going to be important to recognize. Okay, you got to be able to recognize. We're going to first figure out the nonmetal. Then the second nonmetal, use the prefix and the subscripts. Use the prefix, match the subscript before we end up with the name. Okay? All right. Now we're going to move into Lewis structures for molecules. Okay? Lewis structure for molecules. We are going to be using a couple of things. Lewis structures, we talked about already, use what we call symbols and a diagram of the sharing of the valence electrons for single or multiple bonds. This is when it gets a little bit interesting. Okay? Here we have what we call methane. You see the structure of methane. And we'll talk about how that came into formation. So here we have what we call Lewis structures. We'll talk about how to construct these ones, okay? We're going to talk about how we put those Lewis structures together. And here are a couple of Lewis structures. We have methane, we have amine, ammonia, and we have a water molecule. Okay, Lewis structures are used are symbols, diagrams sharing valence electrons for single and multiple bond molecules. So it's going to be important because that starts setting the fundamentals for organic chemistry. Okay, yes, we're getting close to organic chemistry. Covalent bonds. Molecular compounds form when an atom or two non-metals sharing electrons form a covalent bonds, okay? Valence electrons shared by nonmetals to achieve stability. A molecule forms when two or more atoms are sharing electrons. Okay, one of the interesting part is, you might ask, why is it that hydrogen exists as a molecule? Instead of a single element, hydrogen exists with a subscript 2. Let me give you an energy diagram. When you have two hydrogens, they are split without bonding, they're apart, there's no attractions, their energy is high, okay? They're going to attract each other closer, the energy starts getting lower. When you have it on the diet, when they're mixed and they're sharing the electrons, the molecule has a higher stability. So lower energy, more stability. So you see the difference? So that's going to be why they have to exist in a diatomic. So it forms atoms move closer, a positive charge of the nucleus attracts the electrons of the other one, has shared pair electrons to form a covalent bond. Each has a noble gas configuration arrangement similar to helium. Okay, it's more stable than an individual atom. That is why it's so important. You lower down the energy, so that increases its stability. Okay, stability is going to be a lot greater when you exist on a diatomic level instead of two separate hydrogens. It's going to be a lot more in energy. Okay, Lewis structures. A molecule is represented by a Lewis structure in which the valence electrons of all atoms are arranged to give octet, except for hydrogen, which only carries 2 electrons. The number of electrons on a nonmetal atom shares the number of covalent bonds and forms usually equals to the number of electrons needed to achieve noble gas configuration. And that's going to be 8 electrons to get the full valence electrons. The shared electrons or bonding pairs are shown as dots or lines between atoms. The non-bonding pair of electrons, lone pairs, are placed on the outside. Okay, so here we go. We could draw the Lewis structure for molecular compounds. First thing we're gonna start with is with fluorine. Okay, fluorine, if you remember, if we draw the Lewis symbol for each one, it's going to be F and it's going to be 7 electrons, 7 valence electron, because fluorine belongs to group 7. Okay, to achieve 8 electrons for each. Okay, to achieve 8 electrons for each, what they're going to do, the electrons are going to come and they're going to be shared. Okay, so we're going to make a bond. They're sharing a bond, and the rest of them stay as lone pair. So a bonding pair share electrons, and what we call this is equal to a covalent bond. Okay, so this is how the fluorine molecule, and the same thing is going to happen as the hydrogen. You combine those together, the energy is going to be lower, stability, and it's going to have noble gas configuration for both fluorines. Each fluorine shares 1 electron to form a covalent bond, gives each fluorine an octet, and they are going to be happy. Okay, that's how we start building Lewis structures, how structures are going to look. Diatomic molecules. The elements are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine are going to all exist on a diatomic form because it's going to lower the energy and it's going to give all of them an octet rule. Okay, they're all 7 diatomics are going to exist as diatomic molecules because of stability, and you're going to lower the energy. Okay. If we start thinking about drawing Lewis structures, you already saw me draw methane and all this different one, but now we're going to explain where is that actually coming from. So to draw the Lewis structure for methane, Okay, we start by drawing the Lewis symbol for the carbon and the hydrogen. That's the first thing I want you guys to draw. Remember, the carbon symbol is going to be carbon with 4 electrons around, because those are the 4 valence electrons. It belongs to group 4, so it has 4 valence electrons. This one belongs to group 1, hydrogen, the symbol, and 1 electron. Okay? The next thing is the carbon needs 4 hydrogen atoms to complete noble gas configuration for carbon. So it has 4, so it's going to have to find 4 to share. Okay? How do we achieve them? We put one on each side. Okay? We put one on each side. They're going to make 2 sharing. What does that mean? Each hydrogen has 2 electrons. That's fine because that's an exception to the rule. But carbon now has 2, 4, 6, 8. 8 electrons, so it has a 4 electron in its noble gas configuration. Sometimes you will see me draw it with electron pairs, but this actually means 2 electron pairs. This is what we call a sigma bond. Okay? Equals 2 electron pairs. It's the same. They're equal to each other. So carbon needs 4 hydrogen atoms to complete the noble gas configuration. So carbon and hydrogen that's going to be the relationship between. We see other ones, molecules like with Lewis structures. Here's how methane. The same thing with nitrogen. Nitrogen has 5 valence electrons, so it's only going to need 3 hydrogen dots in order to be full in a full octane room. Okay, if you look at this is 2, 4, 6, 8. This is 2, 4, 6, 8. Okay, we'll talk about those lone pairs. Those lone pairs are going to be very important too. Water, oxygen already has 6 because it has 6 valence electrons. It's only going to need 2 hydrogens to be happy because now it's going to have a total of 8 valence electrons. Okay, so that's what they're going to have. That's how their valence electrons are going to be drawn. Okay. Double and triple covalent bonds. A double bond occurs when atoms share 2 pairs of electrons, form when there's not enough electrons to complete an octane. Okay, that's when it gets a little more complicated. Sometimes the valence electrons are not going to be enough. So we're going to have to find a better way to make them fit. So a triple bond also occurs when they share 3 pairs of electrons, form when there's not enough electrons to complete an octane. Let's go over this particular one here. Here we have what we call CO2. The Lewis structure with multiple bonds of CO2. So the first thing we're going to have to figure out is to draw the Lewis structure for carbon dioxide, which the central atom is carbon. Okay. So the first thing we're gonna have to figure out if we need a Lewis structure, and we're gonna have to connect the total valence electrons. The first thing I want you to determine, they already told you carbon is going to be the central one. Okay, so the oxygens are going to be surrounding it. So that's step 1. Step 2 is going to get complicated because now we need to figure out how many valence electrons each one has. We go first with carbon. Carbon belongs to group 4A, so it's going to have 4 valence electrons. Oxygen belongs to the group 6A, so it's going to have 6 valence electrons. But there's something you have to worry. There's 2 oxygens for this particular formula. So you have to worry about it. You have to account. So you have to put a 2 here. So 1 times 4, that's going to be 4 valence electrons there. 6 times 2, 12 valence electrons, a total of 16. So your final molecule has to have 16 valence electrons to be a valid Lewis dot structure. And I'll show you how that actually shows up at the end. Draw the Lewis structure of carbon dioxide, which whenever we said the carbon is going to be the central. Attach each bonded atom to the central with a pair of electrons. Okay, so we will do that. Okay, so if we do that, we're going to draw it here, oxygen and carbon, oxygen there. So we have a total of 4, okay? 4 valence electrons. Still carbon is not happy, oxygen is still missing electrons, so we still got to continue. And we have a total of 16 electrons that we have to use. Okay, whatever valence electrons we calculate, that's what we have to end up with. Okay, next thing we do, use the remaining electrons to complete the octet using multiple bonds if needed. Okay, so you might ask, okay, let's start putting valence electrons here. Okay, let's start putting valence electrons. We start putting valence electrons, and we start noticing that carbon is missing valence electrons, and there is not enough for it to have a full octet. Okay, so what we're going to start doing is we're going to start dumping those electrons here. That's going to give us a double bond. Still, with this structure, just one side is going to be 6, but if you put the other one here, that's why you're going to end up with a full valence electrons. Okay, and let's count it. Okay, let's count them. Now that you put the 2 double bonds in there, carbon has a total of 4 electrons here, 4, that gives it 8. Oxygen has 4 here, 2 here, and that's going to give it 8, so it's going to be happy. Oxygen has 4 on this side, 2 on this side, that's going to be 8, so it's going to be happy. So that's why sometimes we're going to need double bonds or triple bonds in order to be able to stabilize this. Okay, in order to stabilize, to get the right Lewis structure for this particular compounds. Exception to the rule. While the octet rule is useful, there are some exceptions. Hydrogen requires just 2 electrons to form noble gas configuration, so that's one. Non-metals, phosphorus, sulfur, chlorine, bromine can form compounds with 8 to 12 valence electrons. So that was have expandable shells. Okay, they're going to be able to expand because they have d orbitals. The atom has octet many compounds, but it is sulfur 6 fluoride. There are 12 valence electrons, 6 bonds to sulfur. So sulfur is going to be the exception because it's going to be able to handle more electrons.